Hi everybody. We're here getting ready to roll on the last experiment of the semester. This is the SN2 substitution reaction, preparation of hexyl acetate. It's a neat experiment. It's the first experiment that we're doing that's called a preparative exercise. Everything we've done previously has been a technique exercise. We're learning about technique. What you're going to see here in this preparative exercise is many of those techniques are going to come together where the overall goal is to conduct a chemical reaction, isolate, and characterize a product of the reaction. And so the reaction itself is a SN2 substitution. You've learned about that in lecture. We've got 1-bromohexane here. That's our electrophile, a primary haloalkane, a good electrophile for SN2 reaction. Here we've got potassium acetate. The acetate anion there is the critical part for us here. That's our nucleophile. So that electron-rich oxygen is going to donate electrons to the electron-deficient carbon of the primary haloalkane and displace the Br in an SN2 substitution. And that's going to give us an ester as our product. We use DMF as a solvent here. DMF is one of your polar A-product solvents that's good for SN2 substitutions. And then we're also going to be refluxing the reaction, which is where we heat it to its boiling point for a prolonged period of time without loss of material. We'll have more video about the reflux at the time that we actually get that set up. As far as the procedure goes, again, a lot of familiar territory here. The 1-bromohexane, that's a liquid. We actually have a neat dispensing bottle that's going to allow us to dispense that, but you've dispensed liquids before. And then we've got potassium acetate. That's a white powdery solid, and so you've dispensed those before. You'll do that in a round bottom flask, and then we'll do a reflux, and that's a new technique for us, and so we'll have more information about that at the appropriate point in the video. You'll be doing extractions to do the initial isolation of your products from the other byproducts of the reaction. And then we'll be isolating the product by distillation, which you've done before as well. So you can see all of those techniques coming together for the isolation of product. And then once we have the pure product, we'll be characterizing it by infrared spectroscopy, proton NMR spectroscopy, and then the mass spectrum and the carbon-13 and depth spectra are in your laboratory manual. This experiment is also where we begin our preparations for those who are transitioning into Chem 237. Where in Chem 237 we use laboratory notebook entries for the reports rather than report sheets. And so here we're kind of meeting you halfway, where if you've looked at the report sheet for this, it's in the format of a notebook entry. We also have, at this point, an introduction to our notebook guide. So if you look at page 117 through 120 in your manual, it gives you a, sort of an overview of what the expectations for a laboratory notebook entry are, as well as defining some of the specific parts that you'll see as part of a notebook entry. And so from there, if you follow on with that with the report sheet, Dr. Riley will kind of walk you through the report sheet and what that looks like.
Yeah, so the report sheet, again, this is something that you'll be doing on your own in Organic Chemistry 2 in a notebook that has duplicates. So you write on one and it writes on 2 pages at the same time. But essentially, this is our practice to get us used to what we're going to be doing in Organic Chemistry 2 lab. But you have your title, your name, your statement of purpose, and all of these individual points that we're putting in here, there's a statement about them and how to do them in the laboratory notebook guidelines. So the statement of purpose that you're going to write is right here. What do we write there? Well, if we go back to the Organic Chemistry Laboratory Notebook Guidelines, on the back page it says Statement of Purpose. The purpose statement need not be long, but should address all aspects of the exercise. What are you synthesizing? How are you purifying? How are you characterizing, etc.? A reaction equation must be included in the purpose section for exercises that involve a chemical reaction, so etc. So essentially, all of the sections that we put here, you can refer to the guidelines to kind of try and understand what you're going to be putting in there. And then as far as what do you need in that lab report, you also have a rubric. So the rubric is the last page of this experiment, but it essentially says, what are you going to get points for in this experiment? Oh, you wrote your name? Good job, 1 point.
Actually, you wrote your name on the top of every page of the notebook entry, 1 point.
Exactly. So because these notebook entries are supposed to somewhat be preparing us for if we wanted to go work in industry in a laboratory. And it's important in that setting to have the right date, to have your name on every page, because theoretically you might be inventing something new that would be intellectual property. And intellectual property law requires very strict notebook keeping, and we're trying to kind of impress that upon you here. Yeah, and then I mean stuff with data tables. So you guys have all looked at proton NMRs, carbon NMRs. How are we going to show that data in our notebook entry? And we have tables that you would put that into that format, etc. So yeah, this is your first go at the full notebook entry. I think that's kind of it.
Yeah, I think the thing to keep in mind is that the two at this point are meant to be used together. You've got a bunch of blanks in the laboratory notebook report sheet, and to help you fill in those blanks, refer to the guide for that section to see what we're looking for there. So use those two together as you're completing that.
All right. Here is the sodium acetate.
Potassium
Or potassium acetate. See that? There we go.
So we've got the potassium acetate into a 100 milliliter round bottom flask. We put a couple of porous carbon boiling chips in there too. We're going to be boiling it. In the hood here, we've got some dispensing bottles for our dimethylformamide solvent and for our 1-bromohexane reagent. These dispensing bottles have these caps on them that allow you to select a volume that when you raise it and then lower it, it's going to dispense that volume. So right now, the 1-bromohexane is designed to deliver 7 milliliters of liquid. So I'm going to go ahead and raise that up to the stop and then push it down. That dispenses 7 milliliters. The DMF is set up to deliver 10 milliliters, and so I'll need 3 squirts from that. 1, 2, and 3. So now we've got all of our reagents for our reaction in the round bottom flask there. We're going to go set up what's called a reflux apparatus. So here we are in the hood. We've got a reflux apparatus going. If not done this before, so I'm going to talk you through it. It has some similarities to a distillation apparatus. So what we have here is got a ring stand with a clamp on it, a foundation of boards, our heating mantle, our 100 milliliter round bottom flask with our chemicals in it, and then that flask is clamped at the neck. Just like with a distillation, the key support for the apparatus comes from the clamp on the neck of that flask. Now the big difference here is we've got our water-cooled condenser inserted directly into the neck of that flask. The idea of a reflux apparatus is to allow us to heat a mixture to its boiling point for a prolonged period of time without loss of material. So while this is boiling and those hot vapors are rising up in here, once they get into the condenser, they condense and run back down into the flask. So we could heat this for days without loss of material.
We've now refluxed for the given amount of time, and we need to allow the reaction to cool to room temperature prior to doing our extraction. So we're going to turn this off. Heat is off now, and we're going to remove the heat by pulling out these heating blocks. Because we have the reaction supported at that correct location, the neck of the flask, we can just pull that out, and now it'll start to cool down. So now we're going to give it a little while to cool to room temperature, and we will continue with the extraction. Now getting ready for the extraction, I'm going to put the 50 milliliters of water into our separatory funnel, which the reaction will then be added to that. So getting our extraction ready. The reaction now has been adequately cooled. I can hold it with my hand, no problem there. So we're now going to add this to the separatory funnel. The reaction is on this cork ring. I'm going to grab the reaction and I'm going to decant it into this separatory funnel. It already has water in it. So just slowly adding it in there. I'm rinsing the round bottom flask with an additional 10 milliliters of water, and we're going to put that into the separatory funnel as well. So we're getting that. It looked like the solid that was in there went into solution. There was a white solid down there, now it's gone. You can see the boiling chips kind of moving around. Look for the little black piece. It's kind of hard to see. Oh, there we go. There they are. They're the boiling chips. We're going to try and add just the liquid. We don't want to add the boiling chips because they're going to clog the funnel. There we go. Now we're going to add 30 milliliters of cyclohexane to the separatory funnel for this extraction. After shaking the water organic solvent mixture, we now have a separatory funnel that has clearly 2 layers. We can see the interface right there. And we are going to separate the organic from the aqueous layers. We are putting our aqueous layer into this aqueous marked flask. Still going. Gonna see the interface soon. Here it comes. So we'll put the other one in the organic Erlenmeyer flask. We have poured the aqueous layer back into the separatory funnel. Now it's empty, as you can see, because that water aqueous solution is in there, and we are going to extract again with another 30 milliliters of cyclohexane. All right, we now have our combined organic layer that we obtained from our extraction sequence, but it might have a little bit of water still mixed with that organic. So the next thing we're doing is drying with sodium sulfate. Sodium sulfate forms a complex with water. It becomes a hydrate, and that pulls the water out of that organic solution. So that's what we're going to do next. We added our sodium sulfate to the organic layer. Essentially, you know you've added enough when it's no longer clumping. So when I swirl the flask, you can see that some of the solid is still moving around. So if I kind of pull it to the corner like that, you can see that some of that moved to the corner right there. That means that that is not reacting with water, so that means that we have added enough. At this point, we're going to decant this organic liquid into a round bottom flask. And essentially, what does it mean to decant? We're essentially pouring it carefully so that when we pour all of the organic liquid out, the solid will not come with it. So that's the next step. We have now transferred our organic solution from here to the round bottom flask, and now we are going to remove the solvent to leave behind our material. So that's the next step. The procedure next says to remove half of the solvent using a rotary evaporator. So what the heck is a rotary evaporator? So you can see this kind of apparatus that I have in front of me is rotating. So this is our round bottom flask with our material in it. It's rotating, and that is aiding in the evaporation of the solvent. And essentially this apparatus, it can be hooked up to a variety of things. Some of them are hooked up to a water aspirator, but somehow we're going to pull a vacuum in this apparatus. All of the things inside of the glass are sealed, and they are hooked up, in this case, to this vacuum pump over here. Once I turn on the vacuum pump, it's going to pull a vacuum inside of that glassware, and that decreases the pressure. When we decrease pressure, that means that the solvent will evaporate at a lower temperature. So it will allow us to pull off the solvent fairly rapidly. How do we collect the solvent then? So essentially the solvent goes up this glass, comes into here, and these coils, you can kind of see something wrapping around the inside of this. This is cooled with 0-degree water. So there's 0-degree water going through those coils, and that 0-degree water is coming from this bucket over here that you can see is full of ice. So the solvent is going to evaporate, go in the gas phase up this tube. It's going to hit those cold coils and it's going to drip down here. So drip down here into the collection vessel. So I will get another little video showing some of that dripping off of those coils in a moment. All right, so I've already explained the rotovap, but here we can kind of see it in action. The liquid in our round bottom is being heated very slightly in a gentle bath, and the solvent is coming up here, and you can see it is dripping off of those coils that are being cooled by the ice, and that is dripping down into this collection vessel. So you can see there's some liquid in there now, and there was no liquid at the start. So it's a pretty efficient way of removing solvent. We could have just distilled the whole thing as we did in the distillation lab, but this is a faster way to remove solvent than a standard distillation. Here's our solution after the rotovapping. The rotovap probably took off more than half of the solvent, and I'd say around between 3 and 5 minutes or something like that. So it's a pretty efficient way to remove solvent. And now we are going, and yeah, what did we remove? We were removing the cyclohexane that we were using for the extraction sequence. So now we are going to distill off our product with a distillation apparatus. All right, so we've removed more than half the volume of the flask with a rotovap, and now we have a simple distillation setup for isolation of the hexyl acetate. The other component that is still in here is likely some cyclohexane solvent. So when we monitor the reaction, we'll see the temperature kind of start out at the temperature of cyclohexane boiling, because that's going to come off first, and then later on we will see the temperature rise as the hexyl acetate comes off. And what temperature would we expect for that? I haven't looked it up yet.
Yeah, we'll look it up, but at
Yeah,
that
we'll
point,
show you.
switch over to collecting the product into the pre-weighed
pre-weighed
vial.
vial.
15.621 grams is the empty vial with the cap on. All right, we're going to check back in on the distillation here. You can see a nice boil going on inside the flask there, a reflux ring. If we look up at the thermometer, we can see what we're collecting now is coming over at 80.8 degrees Celsius. Keep in mind we have a bunch of cyclohexane solvent in there yet, and we can see that dripping out the end of the distillation apparatus here. We're going to keep that going, and we're instructed that when the temperature gets above 150 degrees that we should switch over to collecting into our pre-weighed vial. So we'll check back in when we get to that point. All right, we'll check back in here. You can see the liquid level is quite a bit lower, and right now our temperature on the thermometer is up around 170 or so. And we started to collect into our pre-weighed vial, and you can see in the beaker there the quantity of the liquid that we collected before it transitioned to be the product. And so we'll be collecting here, monitoring the temperature range that we collect over, and we'll let it go until there's very little liquid left in the distilling flask. Recall you never want to distill to dryness. So we'll check back in when we get the distillation completed. All right, we'll check back in on things here. The distillation is done. You can see the final mass of the product in the vial there at 19.590 grams. Take it out of there and take a closer look at it. You can see we got a nice amount of clear liquid there. This liquid was collected between 170.2 degrees Celsius and 172.8 degrees Celsius. We've got to get an infrared spectrum of the product and a proton NMR spectrum of the product. We'll share those with you once we have them. And then in your manual, you've got the mass spectrum of the product and the carbon-13 and depth spectra of the product. So we'll get back to you with those spectra. Okay, so here we've got the proton NMR spectrum of your hexyl acetate product. Just wanted to talk through it a little bit. We've got 1, 2, 3, 4, 5 good signals for your product. Those are the ones that have the integration values across the bottom and the peak values across the top. What we also have is a little bit of sign of impurity. And so right here you see a couple of little singlets. Those are from DMF.
So that was your reaction solvent. So what happened is some of it made it through the extraction, the organic layer, made it into the distillation, and then was distilled across and collected along with your product. And then this singlet over here, that's cyclohexane. So there again, that was your extraction solvent, made it into distillation obviously, and then just some of it was collected along with your product, not completely separated through that distillation process. So outside of some cyclohexane and DMF, we've got those other signals that are indicative of your hexyl acetate product. We'll get you a better image of this on the Canvas site.
All right, well that concludes the hexyl acetate lab. We have done everything we would need to fill out a full lab report, so you guys will be able to do that. All of the spectral data will be either in the lab notebook, as we have the carbon and the mass spectrum in there, and the proton and IR will be posted on Canvas.
Yeah, that should be it. You know, not the way we envisioned the semester ending. I don't think any of us, but you know, sometimes you just make lemonade out of lemons. So
yeah. So hopefully you enjoyed our very amateur lab productions, and we will, I'm sure, hear from you about all the labs. All right. Goodbye.